So we know we saw that the integral, the area under the curve y equal fx from over the interval EB is equal to the limit of Riemann sum. That means if we take n large, we can approach this area by this finite sum for n large. Now there are many ways to choose the point xi star. For example, when you choose, there is the method we call left point rule. This is when we make the choice, the following choice. When we choose xi star, so left point, so if you consider this interval xi minus 1 xi, the left point will be xi minus 1. Okay, for the right point rule, we make the choice xi star equal the right, so the endpoint xi. Okay, xi, and the midpoint rule, we make in the the following choice, the middle one, so the half of xi minus 1 plus xi. And of course, now it's not just we are guessing and approaching our sum, our integral by this sum. There are studies where we show how the difference, how when we make this approximation, which error we are doing. So we have an estimate of the error we are doing, and there are many methods developed to reach the better, so the lower error mark possible. So depending on the way we are choosing xi star, we are dividing the intervals. So many methods are developed like that. Okay, so an example for the midpoint. Here is an example. So let's, for example, use the midpoint formula with to compute the following integral. Yes, here it is. The integral from 1 to 2 of 1 over x. Yes, here it is. The integral from 1 to 2 dx over x. Okay, with n equal 5. Okay, midpoint with midpoint formula. With n equal 5. So we said it will be then approached by f at so x1 star plus times delta x plus etc. plus fx5 star delta x. So what is, so here is my unit 1 to 2. I need to divide it, so I need 5 subintervals. So this is my x0. Then, so that means I need delta x to know delta x will be 2 minus 1 over 5, which is 1 over 5, 0, 2. Okay, so I move by 0, 2 units. 3, 0, 4, 0, 6, 0, 8, and 0, 2. Okay, so let's say, so here is x1, x2, x3, x4, and this one is x5. Now, where is my x1 star will be here. Okay, this is my x1 star, so it will be x1 plus 1, so it will be 1 plus 1.2 over 2, which is 1.1. Okay, 0, 2 minus 1 over this 5, yes, 0, 5, yes. So I'm moving. X1 is 1, 2, yes. So yes, this is the value, etc. And we do the same here. We will get deduce x2 bar, x star x2 star. So it will be 1.3, and etc. We do that. Okay, so like that, then my value, so it will be f at 1 1 plus f at 1 3 plus f at 1.5 plus f at 1.7 and finally f at 1.9 multiplied delta x is common factor. We saw it, it is then, yes, it's f, it's 0.2, okay, times 0.2, which is 1 over 5. So if you do the calculations, yes, your f, you know it, so it's 1 over 1.1 plus 1 over 1.3, 1 over 1.5 plus 1 over 0.7 plus 1 over 0.9 and etc. 0.2, which is, so we found 0.691908. So this is how it is useful, yes, to have an estimate of the area. Okay, now we would like to develop, we said methods that help us to compute this area exactly. So one of the tools, just by using the definition, we can establish the following theorem. Okay, by knowing simple areas, we can deduce other areas. For example, we can deduce that fx dx will be minus, or let's say from b, if I change the order, okay, from a to b, we can show that it is minus from sorry, I wanted to change here and write it, so it's b to a, it will be minus a to b fx dx. Another okay, so this is more writing. The simplest, this one is AE from the same endpoint. So here delta x is for the sum. Riemann sum is always 0, so that's why the limit will be 0. Okay, then the other one is this one. If you have so this one, we saw it from a to b, a constant dx. We know it's c times e to b 1 dx, and this one, it's easy to show that it's, yes, b minus a, so it's the area of the rectangle. Now we can show that if you have a function multiplied by a constant, and you know the integral of, the area of fx of f over the interval, and you want to deduce the one of c times f, then it's enough to multiply by c. Okay, and if you have the sum of two functions, you have a function, and you see that you can decompose your function as a sum or a difference of two functions, where you know each of them the area under over the interval EB, then we show that it is exactly f plus or minus integral the area under G. Okay. And the other one, this one, intuitively we can now intuitively, geometrically, here is what it is happening. The following is happening. So suppose you have, okay, you have f from e to b, like let's say from e to b, you have your function. Okay, it goes like that, and you want to compute area, but up to c. But then it has another formula, for example. Okay, it has another shape like that. So adding, computing the total area under the function. This is my function y equal fx. Okay, then is adding consists. So we will need to add this plus this area. Okay, we need to add both of them here. Okay. Okay, and this one. Okay, and okay. Let's do it well like that. Okay, so it's the sum of two areas. So this one, if you know that this one is exactly the integral EB of f, and this while this one is the integral from b to c f. Okay, so if we know both of them, then the total area is the sum of the two. This is what we are writing here from E to C, okay, from E to C of f is equal from E to B of f plus integral from B to C of f. Okay, so these are my algebraic operations, very helpful to deduce, yes, when we, depending on the problem we have. Okay, okay. So for example, let's do a quick example here, short example here. So for example here, yeah, we have the following. We are given that the area from over the interval 0, 10 of f is equal to 17. That the area from 0 to 8 of f is 12. So the question is find the area from 8 to 10. Without knowing f, the formula, okay, we are asked to find this value. So here we will use this equality, okay. So I can write from 0 to 10, okay. I can divide my interval from 0 to 8 plus from 8 to 10, and I see that this quantity is the unknown. This is the unknown. I want to know it, okay. So as an equation, so I can deduce then from 8 to 10 will be from 0 to 10 f minus 0 to 8 f, okay. So which is 17 minus 12, which is 5. Okay, so this an application, an idea to have, okay. Now another tool here is comparison. Sometimes it is hard. It's really hard. We can't. There are functions that we don't know how to compute this area. Until now, also we know just for simple functions, maybe constant functions, and maybe a function x. We saw it explicitly manually. We did the calculation. But for more complex functions, we don't know. So we need to know, like we use the approximation, we can use a comparison. So if we have, so first, so this involves the following result. So we have the following result. Let's put it as a theorem. Okay. So we have the following theorem. If you have function f is positive on an interval EB, then necessarily the area under f, okay, from A to B is positive. If you have, we can compare f with another function on an interval EB, then we can compare the area. So visually we can see it, and the proof is not that hard. It uses Riemann sums, and we can do it easily. So you see, so here geometrically you have a function over an interval EB, f. Let's say here is my f, okay, and I am told that we have a function g that is that remains less than. So for any x, the value taken is less than. For any x over the interval EB, the g of x is less than fx. So I might have something like that, okay. This is my function g, y equal g of x. So it is clear that the area under, if you look at the area under g, it's much smaller, okay, is smaller than the area, okay, starting from f, okay. So we have more extra. This is what it says here. So in particular, if you have to compare f with a constant function on EB, okay, then you will have f, okay, from the area is greater than m EB. But this one, m is constant, we know it's mb minus a. So it's a rectangle. If you have your f also less than, so this is bigger than small m, an lower bound. If you have an upper bound, capital M, it will be less than capital M b minus a. Okay, so just correct here, it's small m. Okay, so f is greater than small m times b minus a. Okay, again here also let's do a small example. Let's do a small example here. So for example, what about let's estimate. So we are asked to estimate the definite integral 1 to 4 square root of x dx. Okay, so using Riemann sums, it's not easy. You have a square root function with the sums. It's not easy to find the formula depending on n, that taking the limit. We can of course have an approximate fixing with fixed n approximate value. Let's use estimation also here. For estimation, so we know that you have an idea about the function square root, how it behaves. It's like that. So at 0 takes the value 0, at 1 it's square root of 1 is 1, at 4 you have square root of 4 is 2. Okay, so we are asked to compute the area under these. So this is the area we are interested in. Okay. Okay, so the idea now we want to apply is to bound f between two functions. So the easiest one, of course, is two constant functions. So yes, we can do that. So we can do that. So we know that square root for x, if my x is between 1 and 4, we know that then square root of 1 is less than, is an increasing function. We know those properties. Okay, so we have finally these there's a bound. We bounded our function over the interval 1 4, and then we can deduce that the area then is comparable. We can compare it from 1 to 4. 1 is less than the area from 1 to 4 of the function square root, less than the area under the function constant function 2. So this one will give me 1 times 4 minus 1. This is my integral that I want to bound, and this is 2 times 4 minus 1. So I have here the value 3 minus times 2, 6, and here I have 3, 4 minus 1. So still the estimate is not accurate, it's very large. The difference between 3 and 6 is 3 units. It's too high to say that we have a good estimate, but still sometimes we need it. We need showing that it's bounded is enough. Upper bound showing that it remains, for example, strictly positive or less than this value is important to complete other calculations. Okay, so this is mainly, yes, the tools we developed based on definition. On the definition, we deduced these tools. Okay. Okay.